Section 21.2. The classification of mechanisms. Subsection A. Association, dissociation, and interchange. In this subsection, I will introduce you to three different types of mechanisms for the ligand substitution reactions: dissociative, associative, and interchange mechanisms. In each of the three types of mechanisms, there are two steps, but these two steps are different. So first, let's look at this dissociative mechanism. The first step is dissociation. We first break the MX bond, and now you have this free X, and then this entering ligand forms a bond with the metal. So two steps. The first step is dissociation. Now let's look at the intermediate. It consists of three particles. X, the leaving group, now is free in the solvent. Y, the entering group, is also free in the solvent. And now this M. For simplicity, we're not putting ML sub n here, but this is really ML sub n. So this M can be bonded to and are often bonded to some other ligands. Alright? But then our focus is on the leaving group and the entering group. So that's why we didn't put LN here. This is the transition state of the first step. This is the transition state of the second step. So if you know the Gibbs energy of this one and this one, take the difference, you get delta G double dagger, and then you can use our Arrhenius equation, kBt over H times e to the power of negative with delta G double dagger over RT to compute this reaction rate. Alright, and same here, you can compute the reaction rate constant. Associative mechanism. Again, there are two steps, but these two steps are different from these two steps. Just from the name, associative mechanism. Well, the first step is association. So look at the first step. Y forms a bond with the transition metal. That's it. So X has not left yet. Now if you look at the intermediate, in this case, this transition metal center is bonded to both X and Y. Alright? So it might be a little crowded here, but M is bonded to both X and Y. The second step, X leaves. Okay, that's the second step. Again, this is called intermediate. Okay, it's trapped in the well here. So if you freeze this entire reaction, it's possible to isolate this X, M, Y intermediate. Alright? So as long as you freeze this entire reaction mixture, it's possible to be able to isolate this out of the mixture. Same here. Okay, so this is dissociative mechanism. So again, if you freeze the entire reaction mixture, you'll be able to somehow isolate this M. It's actually MLN. It's not bonded to X or Y. Okay, so it's just ML sub N, not bonded to X or Y. Over here, M is bonded to both X and Y. It's a higher energy intermediate species, but it can be isolated if you freeze this reaction mixture. And there are also two transition states. This is the transition state of the first step. This is the transition state of the second step. This is called associative mechanism because in the first step, you have this Y bonded to M, and X has not left yet. The third type, interchange mechanism. Alright, the shorthand notation is I. Well, over here it's A. Over here it's D, dissociative. D, associative. A, interchange. I. So you have DAI, associative, dissociative, interchange. Okay, now look at here. Also, we're focused on the first step. In the first step, well, it's kind of interesting. So it's kind of between the dissociative and associative mechanisms. So X starts to leave, but X has not completely leave. It's a partial bond between X and M in the intermediate. Y starts to enter, but the bond between Y and M is also not a complete bond. It's a partial bond. So in this intermediate, M forms two partial bonds, one with the leaving group X, the other with the entering group Y. So that's why this is called interchange mechanism. In the second step, well, X leaves completely, and Y forms a complete bond with M. So over here, the intermediate is X partial bond M, M partial bond Y. And this is also a intermediate which is trapped in this well. The depth of this well is usually shallower, more shallow than this one or this one. Okay, so it's more difficult to isolate this intermediate. But again, if you freeze this reaction mixture fast enough to a very low temperature, it's possible to isolate this species X partial bond Y partial bond partial bond M partial bond Y. All right, and also there are two transition states: the transition state for the first step, the transition state for the second step. So again, three mechanisms: associative A, dissociative D, and interchange mechanism I. The difference is the intermediate. Dissociative mechanism involves a intermediate with M, X, and Y all separated from each other. Over here, associative, M is bonded to both X and Y. Interchange, this is in the middle. M has a partially broken bond with X and partially formed bond with Y. Subsection B, the rate limiting step. The rate limiting step is the slowest step in a sequential mechanism. All right, how do you know it's a sequential mechanism? Well, it's very simple. A sequential mechanism involves multiple steps, at least two steps. All right, and then if you somehow block one of these multiple steps, this reaction cannot proceed at all. But in a parallel mechanism, for example, you can go from A to B and then A to C. These two are in parallel to each other. So if you break the A to B step, A to C can still proceed. But in a sequential mechanism from A to B to C, so in this case, A to B to C, if you break the B to C step, you can no longer form the final product C. If you break the A to B step, you can no longer form the product C. So that's the difference between sequential and parallel. So now let's look at this associative, dissociative, and interchange mechanism in the previous subsection A. This is sequential. So if you break this channel, it's going to stop here. You're not going to form the product. Same here. If you break here or break here, you're not going to form the product. If you break here, you're not going to form the product. So all three are sequential mechanisms. All right. And then in a sequential mechanism, the slowest step is the rate limiting step. The rate limiting step can be classified as associative or dissociative. It depends on which step is the slowest step. So now let's look at this energy diagram. So over here, you can see this is a associative mechanism, right? So if you look at the intermediate, M is bonded to both X and Y, and both bonds are complete bonds. So this is a associative mechanism. And now let's look at the rate limiting step. Basically, we just look at the energy difference between the transition state and the reactant. So over here you have activation energy. Okay, from here to here, that's activation energy of the first step. We also have the activation energy of the second step from here to here. Now you can see the first energy barrier or activation energy is larger than the second one. That means the first step is slower than the second step. All right? There are only two steps. The first step is slower than the second step, and therefore the first step is the rate limiting step. And in the first step, well, it's a association reaction, right? So you start from two particles, you form only one particle, it's association. So in this case, we say, well, the first association step is the rate limiting step. And then we say it's associatively activated. All right, so this mechanism is association mechanism by looking at the intermediate. And it happens to be associatively activated because the first association step has the largest energy barrier and is the slowest step in this sequential mechanism. So that's why we say this is associatively activated. All right, we'll focus on this rate limiting step later. Okay, now this one. Still, you look at the intermediate and say, well, this is associative mechanism because in the intermediate species, M is bonded to both X and Y. Okay, but then in this case, if you're looking at the slowest step, it's the second step, right? It's the second step. Why? Well, if you look at the second step, you have a larger activation energy than that of the first step. So the second step is the slowest step in this sequential mechanism. So that's why we say, well, this step is the rate limiting step. And then you look at the nature of the second step. It's a dissociation reaction. So over here, there's a bond breaking reaction. MX bond is broken in the second step. Because the bond is broken, you start from only one species, you end up with two species. We say this is a dissociation reaction or a dissociation step. And because this dissociation step is the rate limiting step, we say this mechanism is called dissociatively activated mechanism. So again, it sounds strange. It's a association mechanism, but also it's dissociatively activated because we're talking about two different things. When we are saying it's a association mechanism, we are referring to the intermediate species. In the intermediate species, we have M bonded to both X and Y. Both bonds are complete bonds, whole bonds. All right, so that's why it's association mechanism. But then you need to identify the slowest step and just examine the slowest step, whether that slowest step is an association reaction or dissociation reaction. So over here in the slowest step, okay, it's association. Therefore, it's associatively activated. Now look at this slower step. It's dissociation, therefore it's dissociatively activated. Now let's look at these two diagrams. First, let's examine the intermediate. X, Y, M, all separated. X, M, Y, all separated. So these two, both are dissociative mechanism. Okay, both are dissociative mechanism by checking the intermediate. Now let's look at the slowest step with the largest energy barrier. In this case, the second step has the largest energy barrier, and in the second step, it's an association reaction. So from M and Y, you get M bond Y. All right. So you start from over here 3 particles. Now you end up with only 2 particles, 2 species. So it's a association reaction, and this association step is the rate limiting step. So this is associatively deactivated. Okay, now same dissociative mechanism. But in this case, the first step has the larger energy barrier and is slower. And also in this step, you can see it involves the bond breaking between X and M. So it's dissociatively activated. All right. So again, both are dissociative mechanism. Over here, this is associatively activated. This one's dissociatively activated. Okay, I'll let you look at the figure captions over here. And this A sub A and then D sub A, it means over here, this is associative mechanism, and this is dissociative mechanism. And then you look at the subscript, this lowercase a in subscript. That means it's associatively activated. Associatively activated. All right. So this limiting step is association. This limiting step is association. Now look at this figure caption. You have associative mechanism A, dissociative mechanism D, and then you need to look at the subscripts. Okay, lowercase d and d. That means these two are dissociatively activated. All right, so you have this is associative mechanism, but the rate limiting step is dissociative. This is a dissociative mechanism, and if you look at this slowest step, it involves dissociation, so it's D sub D. You have A sub D and D sub D. Over here, A sub A and D sub A. Okay. Finally, interchange mechanism. You just need to look at the intermediate. In the intermediate, you have this MX bond partially broken, MY bond partially formed. Same here, MX bond partially broken, MY bond partially formed. Okay, over here, intermediate. And then you have two changing states, this two changing states, trapped this intermediate in the NH well here, and also here. Now, which one is associatively deactivated, which one is dissociatively deactivated? You need to look at the two steps in the sequential mechanism. Whichever step has the largest NH barrier or activation energy is the rate limiting step. So now let's look at this. This one is the rate limiting step, right, with a larger barrier. Over here, the second step is the rate limiting step with a larger barrier. And then let's just count the number of species. 2 species, 1 species. So this is, well, associative. Over here, look at this rate limiting step. 1 species here, 2 species here. So it's dissociative. Now we can have I sub A. This is interchange mechanism, associatively activated, and this is also interchange mechanism, but dissociatively activated. All right, so it's I sub A, I sub D. Okay, this is I sub A. The slowest step involves association. This is also interchange mechanism, but the slowest step is dissociation. So it's I sub D here, I sub A on top. Now let's look at the ligand substitution reactions in a square planar complex. The reason we look at this is because for a square planar complex, it's kind of interesting that although you may do experimental measurements and you may find that this reaction rate is first order. Okay, it's just proportional to this one. Sometimes it's a truly first order reaction. Sometimes it's just a combination of first order and second order. And why is that? I'm going to explain. When you have a square planar complex, so this metal is bonded to only 4 ligands in the same plane. So it is possible for a entering group to approach this metal from top or from the bottom. So it's possible for this reaction to be a second order reaction. The reaction rate is proportional to the concentration of this reactant transition metal complex, and also proportional to the concentration of the entering ligand. So that's second order. But also it can be first order. Well, what if this transition metal breaks a MX bond first? Okay, and it happens to be the rate limiting step. And then, well, the kinetics is limited by this rate limiting step. The bond breaking between M and X is the rate limiting step, and that's the first order. So now let's look at this reaction. Again, Y is going to replace X in this transition metal complex. And I put dot here because I don't know what the pathway is. And there can be multiple pathways. The product is this, okay? X is the leaving group, Y is the entering group. But the reaction rate can be a combination of, this is first order reaction rate, this is the second order reaction rate. Over here, this is proportional to two chemicals, the concentrations of two chemicals. Alright, so over here, I'm saying that the rate limiting step could be the bond breaking of M and X. And in this case, there's only one reactant, just this one, in this rate limiting step. And also, we may have a associatively activated mechanism. Okay, so it's possible that this Y enters here, and this intermediate state involves this M with two bonds with X and Y at the same time. And in that case, we have two reactants, one this, and in that case, I want to say, well, this is a second order reaction. So we have another term here. And both the first order and second order reactions can proceed at the same time. Well, nothing prevents this transition metal to go through these two different reaction pathways. So in that sense, we are looking at two parallel reaction mechanisms. One is first order, the other is second order. All right? So both reaction pathways lead to the same product. So both should be taken into account. However, sometimes when we have a very high concentration of M, the concentration, very high concentration of Y, the entering ligand, we can assume the concentration of Y does not change significantly throughout the entire reaction. So this Y is roughly a constant, right? So one example is if you just put a, let's say, transition metal complex with some very weak field ligand, put that in water, and those weak field ligands can be replaced by the aqua ligands, right? And then, there are two different pathways. One pathway is the first order reaction. The metal breaks the bond with one weak field ligand first, and then a water comes in. Or the water can come in and form one more bond with the transition metal, right? And in that case, we have both first order and second order reaction pathways going on at the same time. And also, if this reaction is done in water, water is the solvent. So, and water also react with the transition metal complex. How does the reaction changes the concentration of water? There's no change. The water concentration remains unchanged as the reaction proceeds. Okay, approximately, right? Approximately. So you can imagine you have tetrachloride platinum or platinate 2 dissolved in water. Let's say we're using water to replace the chloride ligands, and then, well, the chloride ligands will leave the transition metal complex and get dissolved in water. Does that change the concentration of water? Maybe a little bit. Okay, water is roughly 55.5 mole per liter if it's pure water. But then if you have transient metal dissolved in water, you have chloride leaving the transient metal, that will slightly reduce the concentration of the water solvent. But still, I'm going to say it's roughly 55.5 molar. All right. Okay, why 55.5? Well, it's just 1 liter of water weighs 1,000 grams. That's roughly 55.5 moles. So that's why. So in that case, I just want to emphasize the real mechanism is the sum of two reaction pathways, first order and the second order. Okay? But experimentally, when you measure this reaction rate, it seems that this reaction rate is only proportional to this reactant, the initial transition metal complex to the power 1. So you might be fooled by your experimental data and think it's a first order reaction, but really it's a so-called pseudo first order reaction. It's actually a complex reaction mechanism that involves two different pathways, first order and the second order, at the same time.